the star that disappeared. After eons of cosmic wandering, our time-traveling observers have arrived at a moment that will forever change our understanding of stellar death and the violent birth of the most mysterious objects in the universe. These ancient witnesses are no strangers to cosmic drama. They've watched galaxies collide, witnessed the birth of solar systems, and observed the spectacular deaths of countless stars. But this visit will reveal something unprecedented. The moment when a massive star simply vanished without a trace, challenging everything we thought we knew about how the universe's most extreme objects come into existence. In 2009, astronomers were monitoring a luminous blue variable star, designated N6946-BH1, located 22 million light-years away in the Fireworks Galaxy. For years, this stellar giant burned brilliantly, one of the most massive stars in its galaxy. Then, between 2009 and 2015, something extraordinary happened. The star simply disappeared. No supernova explosion, no expanding nebula, no spectacular light show. It was there, and then it wasn't. Join Eclipse Unknown and our cosmic observers as we unravel one of astronomy's most perplexing mysteries, explore the hidden mechanisms of stellar collapse, and discover what happens when the universe's most massive stars meet their end, not with a bang, but with complete and utter silence. The Vanishing Act. This disappearing act isn't unique in the cosmic theatre. Astronomers have now documented several similar cases. So what makes these stellar vanishings so extraordinary? When most massive stars die, they announce their demise with spectacular supernova explosions that can outshine entire galaxies for months. These cosmic fireworks occur when a star's core can no longer sustain nuclear fusion, causing catastrophic collapse followed by a tremendous rebound explosion that hurls the star's outer layers into space. But some stars appear to skip this dramatic finale entirely. Instead of exploding, they seem to implode so completely that they disappear from view, leaving behind only the most enigmatic objects in the universe, black holes. This process, known as failed supernova or direct collapse, was predicted by theoretical physicists decades before we had any observational evidence. N6946-BH1 was a perfect candidate for this phenomenon. With an initial mass estimated at 25 times that of our Sun, it belonged to a class of stars known as luminous blue variables, massive, unstable giants that fluctuate dramatically in brightness. These stellar behemoths live fast and die young, burning through their nuclear fuel in just a few million years compared to the Sun's 10 billion-year lifespan. What makes N6946-B H1's disappearance so remarkable is that astronomers watched it happen in real time. Between 2007 and 2009, the star brightened significantly, suggesting it was entering its death throes. Then, monitoring observations revealed a dramatic fade. By 2015, deep imaging with the Hubble Space Telescope confirmed what seemed impossible. The star had vanished completely, leaving behind only a faint infrared source that could be the warm dust of a newly formed black hole. The physics of stellar suicide. But what causes a star to collapse so completely that it can't even produce a supernova explosion? The answer lies in the delicate balance between gravity and the outward pressure generated by nuclear fusion. Throughout a star's life, these forces exist in equilibrium, gravity trying to crush the star inward, while fusion reactions push outward with tremendous force. As massive stars age, they create increasingly heavy elements in their cores through nuclear fusion. First hydrogen fuses into helium, then helium into carbon and oxygen, followed by neon, silicon, and finally iron. Each successive fusion stage produces less energy and occurs more rapidly. The silicon burning phase that creates iron lasts only days. Iron presents a unique problem. Unlike lighter elements, iron fusion actually absorbs energy rather than releasing it. When a star's core becomes predominantly iron, fusion suddenly stops providing the outward pressure needed to support the star's enormous weight. Gravity wins decisively. In a typical supernova, the core collapses to neutron density in less than a second, creating a shockwave that rebounds outward and tears the star apart. But in the most massive stars, those above approximately 40 solar masses, something different happens. The core collapse is so violent and the resulting black hole forms so quickly that the shockwave never has a chance to propagate outward. Instead, the entire star falls past the event horizon, disappearing from the observable universe forever. This process happens with breathtaking speed. Once iron fusion begins absorbing energy instead of producing it, the star has less than 24 hours to live. The core collapse itself takes mere milliseconds. Faster than the speed of light can carry information from the core to the star's surface. By the time the star's outer layers realize what's happening, they're already falling inward past the point of no return. The cosmic census. Here comes the truly staggering realization, and it fundamentally changes our understanding of stellar evolution. How many massive stars die this way? What fraction of the universe's stellar giants vanish without a trace, directly forming black holes instead of exploding as supernovae? Current estimates suggest that between 20% and 30% of massive stars may undergo direct collapse rather than exploding as supernovae. This has profound implications for our understanding of black hole formation and the chemical evolution of galaxies. Supernovae are cosmic recycling plants, dispersing heavy elements created in stellar cores throughout the galaxy. These elements eventually become incorporated into new stars, planets, and even living organisms. When massive stars disappear through direct collapse, they take all their heavy elements with them, removing them permanently from the galactic ecosystem. This process, called stellar necrophagy, literally star-eating, means that the universe may have lost significant quantities of carbon, oxygen, silicon, and iron to black holes throughout cosmic history. The implications extend beyond individual galaxies. The rate of direct collapse versus supernova explosion affects the overall metallicity of the universe, the abundance of elements heavier than hydrogen and helium. Computer simulations suggest that without failed supernovae, galaxies would contain significantly more heavy elements than we observe today. The search for silent deaths. Detecting these stellar disappearances requires patience, precision, and a bit of luck. Unlike supernovae, which announce themselves with brilliant flashes of light, failed supernovae are defined by absence, the gradual fading and eventual disappearance of a star that should still be burning brightly. The most systematic search for these events is the GALEX survey, which uses ultraviolet observations to monitor massive stars in nearby galaxies. UV radiation is particularly sensitive to the hot, massive stars most likely to undergo direct collapse. By comparing observations taken years apart, astronomers can identify stars that have mysteriously vanished. One of the most compelling cases after N6946-BH1 involves the star N6946-BH2, also in the Fireworks galaxy. This star, initially 20 times more massive than the Sun, underwent a similar disappearing act between 2007 and 2015. The consistency of these observations in the same galaxy suggests that failed supernovae may be more common than previously thought, but confirmation remains challenging. The infrared glow that potentially marks a newly formed black hole is extremely faint and could be explained by other phenomena. Dust clouds, background galaxies, or even instrumental artifacts could mimic the signature of stellar collapse. Astronomers need multiple independent observations spanning several years to confirm each case. Advanced space telescopes are revolutionizing this field. The James Webb Space Telescope's unprecedented infrared sensitivity allows astronomers to peer through dust clouds and detect the faint thermal emission from failed supernovae. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will monitor millions of stars simultaneously, potentially catching stellar disappearances as they happen. The Black Hole Factory. What our cosmic observers find most remarkable is how these stellar vanishing acts represent the universe's most efficient black hole production mechanism. While stellar mass black holes can form through various processes, direct collapse creates the most massive specimens, black holes with masses 20 to 100 times that of our Sun. These stellar mass black holes are fundamentally different from their supermassive cousins that lurk at galactic centers. Supermassive black holes, containing millions or billions of solar masses, likely formed through different mechanisms in the early universe. Stellar mass black holes from failed supernovae represent the endpoints of individual stellar evolution, the final fate of the most massive stars. The properties of these directly formed black holes remain largely mysterious. Do they retain the rapid rotation of their progenitor stars? How quickly do they begin accreting matter from their surroundings? The answers could help astronomers distinguish between black holes formed through direct collapse versus those created by supernova explosions, followed by neutron star collapse. Gravitational wave detectors like LIGO and Virgo have revealed that stellar mass black holes are more common than previously thought. The black hole mergers detected by these instruments often involve objects more massive than theoretical models predicted for supernova-formed black holes. Failed supernova may explain the origin of these unexpectedly heavy black holes. The progenitor problem. Understanding which stars undergo direct collapse requires unraveling one of astrophysics' most complex puzzles: the relationship between a star's initial mass and its ultimate fate. This isn't simply a matter of more massive stars make bigger black holes. Stellar evolution involves intricate feedback loops between nuclear burning, stellar winds, rotation, magnetic fields, and chemical composition. Stars above approximately 40 solar masses are prime candidates for direct collapse, but the exact threshold depends on metallicity, the abundance of elements heavier than hydrogen and helium. Lower metallicity stars retain more of their mass throughout their lives because they produce weaker stellar winds. This means that stars of identical initial mass might meet different fates depending on when and where in the universe they formed. Stellar rotation adds another layer of complexity. Rapidly spinning massive stars experience centrifugal forces that affect their internal structure and evolution. Fast rotation can prevent core collapse by providing additional support against gravity, potentially saving a star from direct collapse and allowing it to explode as a supernova instead. Binary interactions further complicate the picture. Many massive stars exist in close binary systems where they exchange mass with their companions. These interactions can strip away the hydrogen envelope that might otherwise fall into a black hole during direct collapse, potentially converting a failed supernova into a successful one. The stellar graveyard. For the first time in cosmic history, during these observations, intelligent beings, humanity, possess the technology to witness and catalogue these stellar deaths in real time. Our ancestors could observe supernovae with naked eyes, recording guest stars that appeared suddenly in the night sky. But failed supernovae remained completely hidden until the advent of modern astronomical surveys. Today's automated sky surveys monitor millions of stars nightly, creating an unprecedented catalogue of stellar behaviour. The Catalina Real-Time Transient Survey, the all-sky automated survey for supernovae, and similar programs generate millions of observations annually. Machine learning algorithms sift through this data, identifying anomalous behaviour that might indicate stellar disappearances. This technological capability comes at a crucial time in astronomical history. The universe's most massive stars are becoming increasingly rare as cosmic star formation rates decline. The peak of star formation occurred approximately 10 billion years ago, meaning the most massive stars from that era are now reaching the ends of their lives. We may be witnessing the final chapter of the universe's most spectacular stellar deaths. Space-based observations provide unique advantages for detecting failed supernovae. Earth's atmosphere blocks much of the ultraviolet and infrared radiation that characterizes massive star evolution. Telescopes like Hubble, Spitzer, and now James Webb offer unobstructed views of stellar death throes across the electromagnetic spectrum. The galactic impact. While individual stellar disappearances might seem like isolated cosmic events, their cumulative effect shapes galactic evolution over billions of years. Each failed supernova removes potential stellar feedback, the energy and momentum that massive stars inject into their surroundings through stellar winds and supernova explosions. This feedback plays a crucial role in regulating star formation. Supernova shockwaves compress nearby gas clouds, triggering new star formation while simultaneously heating and dispersing gas that might otherwise collapse to form stars. The balance between these competing effects helps determine a galaxy's overall star formation rate. Galaxies with higher rates of failed supernovae might experience reduced stellar feedback, potentially leading to more efficient star formation and different galactic structures. Computer simulations suggest that the ratio of successful to failed supernovae could explain some of the observed diversity in galaxy types and properties. The gravitational effects of stellar mass black holes also influence galactic dynamics. While individual black holes are too small to affect galactic rotation curves, their collective gravitational influence contributes to the overall dark matter budget. In galaxies with particularly active star formation histories, stellar mass black holes could represent a non-negligible fraction of the total mass. The missing supernovae problem. One of the most intriguing implications of stellar disappearances relates to the missing supernovae problem. The discrepancy between theoretical predictions of supernova rates and actual observations. Based on stellar evolution models and observed star formation rates, astronomers expect to see more supernovae than they actually detect. Failed supernovae provide a compelling solution to this puzzle. If 20 to 30% of massive stars undergo direct collapse instead of exploding, it would perfectly explain the deficit in observed supernova rates. This concordance between theory and observation strengthens the case for stellar disappearances as a real and significant phenomenon. The missing supernovae problem has important implications for using supernovae as cosmological tools. Type Ia supernovae, which result from white dwarf explosions, serve as standard candles for measuring cosmic distances, and were instrumental in discovering the acceleration of cosmic expansion. Core collapse supernovae from massive stars provide complementary information about cosmic star formation history. If a significant fraction of massive stars fail to produce observable supernova, it affects our interpretation of supernova surveys and their implications for cosmology. The apparent decline in supernova rates at high redshift might partially reflect an increase in failed supernova rates rather than decreased star formation. Future discoveries. As our cosmic observers prepare to continue their eternal journey, they wonder what new revelations await in the realm of stellar death. Next-generation telescopes and survey programs will revolutionize our ability to detect and study stellar disappearances. The extremely large telescope, currently under construction in Chile, will have unprecedented resolution and sensitivity for studying individual stars in nearby galaxies. Its 39-meter primary mirror will collect 13 times more light than current ground-based telescopes, allowing astronomers to monitor stellar populations in galaxies tens of millions of light-years away. The Vera C. Rubin Observatory will begin operation soon, conducting the Legacy Survey of Space and Time, LSST. This ambitious project will photograph the entire southern sky every few nights for 10 years, creating a time-lapse movie of the universe. LSST will likely discover hundreds of stellar disappearances, providing the statistical samples needed to understand failed supernova rates across different galaxy types and cosmic epochs. Gravitational wave astronomy offers another window into stellar collapse. While failed supernovae might not produce detectable gravitational waves during the initial collapse, the resulting black holes could eventually merge with other compact objects, producing signals detectable by current and future gravitational wave observatories. Multi-messenger astronomy, combining optical, infrared, X-ray, gamma-ray, neutrino, and gravitational wave observations, will provide unprecedented insights into stellar death. Future neutrino detectors might even detect the brief neutrino burst produced during the core collapse that precedes stellar disappearance. The ultimate fate. Perhaps the most profound question our alien observers contemplate is what stellar disappearances reveal about the universe's ultimate destiny. Every failed supernova represents matter permanently removed from the observable universe, falling past event horizons into regions where even light cannot escape. As the universe ages and stellar formation declines, an increasing fraction of matter may become locked away in black holes. The cosmic recycling provided by supernovae will eventually cease as gas supplies are exhausted and stellar formation stops. At that point, stellar disappearances will represent pure loss, matter vanishing from the universe's inventory forever. Hawking radiation provides a potential escape mechanism, but only over timeframes that dwarf the current age of the universe. Stellar mass black holes require approximately 10 to the power of 67 years to evaporate completely through Hawking radiation. Long before that happens, the last stars will have burned out, leaving behind a cold, dark universe populated only by black holes, neutron stars, and elementary particles. Yet even in this far future, stellar disappearances continue to fascinate. The black holes formed by failed supernovae will be among the longest-lived objects in the universe, outlasting protons themselves if current theories about particle decay prove correct. In a sense, the stars that disappeared today will be the universe's final witnesses to the age of stellar fire. Conclusion. As our time-traveling observers fold space-time around themselves and prepare for their next cosmic destination, they carry with them the profound realization that sometimes the most important events are marked not by spectacular displays, but by haunting silence. The stars that disappeared represent one of nature's most elegant solutions to the problem of extreme gravity. When the force becomes too strong for even nuclear fire to resist, matter simply steps outside the bounds of observable reality. These stellar vanishing acts remind us that the universe operates by rules far more complex and mysterious than our everyday experience suggests. The same physical laws that govern falling apples and orbiting planets also dictate that sufficiently massive stars must eventually disappear completely, taking with them all record of the nuclear furnaces that once burned in their cores. What captivates our cosmic visitors most is how these disappearances represent both an ending and a beginning. While the visible star vanishes forever, it leaves behind something far stranger, a gravitational wound in space-time itself, a black hole whose influence will persist for eons after the last conventional star has burned out. In the far future, when the universe has grown cold and dark, these stellar ghosts may be all that remains of the age when massive stars lit up the cosmic night. When our alien observers return to this corner of the universe in the distant future, will they find galaxies still populated by burning stars? Or will they discover a cosmos where all the massive stars have long since vanished, leaving behind only the invisible signatures of their gravitational graves? The stars that disappeared today are writing the opening chapters of that far future story, one silent collapse at a time.